So rates 2017 paper 2. So what have I got here? I've got concentration up the side, time along the bottom. If it were a straight line, it would be order 0 because we can measure tangents to the curve at different concentrations, different initial concentrations. But it's not a straight line, so it's definitely not 0. It's some kind of curve, so the gradients are changing as we change the initial concentrations, and so therefore concentration is having an effect on the rate. What's it actually asking me to do? Draw a tangent to the curve at time t0. So you draw that, you make sure it intercepts both of the axes. You measure the change in y from 0 up to 0.5. You measure the change in x from 0 to 10. 0.5 divided by 10 is 0.05. And it's coming down. So if it's coming down in that kind of shape, it's a minus gradient. Although they wouldn't have marked you off for putting it as a plus gradient. But it is a minus gradient because it's coming down. If it goes up from left to right, it's a positive gradient. Okay. The experiment was repeated at the same temperature. Okay, so the rate constant is going to stay the same, and with the same initial concentration of B with a different concentration of A. The new initial rate was 1.7 times greater than the original experiment. Calculate the new initial concentration of A. So, a tricky one, really. Rate equals K multiplied by concentration of A squared and multiplied by concentration of B. It's given you that in the first part of the question. It says B is unchanged, but the rate has increased by 1.7 times. So, rate constant is not changing because the temperature hasn't changed. B is not changing because it tells you that in the question. So, if rate has increased by 1.7 times, and K, the rate constant, stayed the same because the temperature stayed the same, B stayed the same because it tells you that in the question, then A squared must also have increased by 1.7 times because everything else is staying the same. So A squared has increased by 1.7 times, square root of A has increased by 1.3 times. Okay. It's asking you for the initial concentration of A. So, from the first experiment, the initial concentration of A was 0.5 because it tells you that that's where the curve hits the y-axis. So the initial concentration of A was 1.5 times, but A has increased by 1.3 times. So if in the first experiment the concentration of A was 0.5, the initial concentration from the graph was 0.5, and it's increased by 1.3 times. 0.5 times 1.3, 0.65 times. So, the new concentration of A is 0.65, 1.3 times the original concentration of 0.5. Everything's to two significant figures, so let's put it to two significant figures, 0.65. Yeah, that's fine. A series of experiments is carried out on compounds C and D using the data contained in the rate equation is as such: rate equals K, C concentration multiplied by D concentration. In one experiment, the 25 degrees C, that's irrelevant, the initial rate of the reaction is giving you the rate, okay, 0.031, 3.1 times 10 to the minus 3. When the initial concentration of C is 0.48, initial concentration of D is 0.23. Oh, they're just asking you to plug the numbers in and work out what K is, 0.028, really straightforward. And then it's asking you for the not just the value of the rate constant at this temperature, give its units. Oh, straightforward question. Moles divided by decimeter cubed with the second on the bottom as well. Moles divided by decimeter cubed divided by seconds is K And then we've got two concentrations, C and D, so it's moles divided by decimeter cube, moles divided by decimeter cube. Take the 2 decimeter cube from the bottom on one side, put them on the top on the other. 2 moles on the top on one side, drop them onto the bottom of the other. Cancel, and you end up with mole per decimeter cube on the top and a mole and a second on the bottom. Put it into standard form, so it's decimeter cubed, mole to the 1 becomes mole to the minus 1, second to the 1 on the bottom becomes seconds to the minus 1, decimeter cubed, mole to the minus 1, second to the minus 1, in any order you wish. Arrhenius, what's it actually asking you? Just to plug some numbers in. So this is plug the numbers in. Remember, there's 2 kinds of Arrhenius. They'll either get you to draw a graph of ln k over 1 over t, and the gradient is minus EA over R. But in this case, they're just asking you to plug some numbers in. So they've given you k, they've given you ln(a), they've even given you the ln(a), so you have to do ln of 0.028, needs to be calculated on the ln, natural log button, equals minus EA over R, which is 8.31. Have they given you temperature? Yes, they have. Oh, they've given you in 25 degrees C, and temperature needs to be in Kelvin, so you have to add on 273 to work out 298. Okay, don't forget to put your temperature in Kelvin, add ln(a), rearrange it, so take the minus 16.9 across the other side, multiply by 8.2, 8.31 and 298 on each side, and you'll come up with minus EA is minus 50716 joules. They want it in kilojoules. Okay, let's make the EA positive, so positive EA is positive 50716, multiply by 1,000 to get, so divide by 1,000 to get joules into kilojoules, and put it to the correct number of significant figures, which is 2, 51 kilojoules per mole.